Welcome to another Heatwise tutorial on psychrometrics. This is the fourth and final psychrometrics video. So in this video we'll be going over an example from start to finish, going through the mixing of air streams and then dehumidifying, so latent and sensible cooling, and then sensible heating up to a supply air state for a particular air stream. And then we'll be determining the total sensible and latent cooling required for that process, as well as the sensible heating power necessary to achieve the final state. So before getting into the air states and the calculations of cooling and heating, we'll first start with the altitude adjustment. So we're going to assume that this example is not at sea level, which means we'll have to pick an altitude. So we'll just say for this example we'll have a 1500 foot altitude. So we need to adjust our pressure relative to atmospheric pressure at sea level. So that is with our equation that was introduced in a previous video. So we have P over P0, P0 being sea level atmospheric pressure. And that is equal to 1 minus 6.8754 times 10 to the minus 6 multiplied by our altitude in feet. And this is to the power of 5.2559. And this results in 0.947 as our ratio of our pressure at our location to the atmospheric pressure at sea level. So with that value, we can now carry on to our actual psychrometric calculations. So we're starting with the mixing. So for this example, we will assume that we need a total supply flow of 6,000 CFM. And this would come from our load calculations. So our load calculations tell us that we need 6,000 CFM. And our outdoor air calculations tell us that we need 1,500 CFM. Again, these would be done with other calculations that are out of the scope of this video, so we're just going to assume that these were done elsewhere. So if we have 6,000 supply and 1,500 outdoor air, that means our return airflow is going to be 4,500. So these are our airflow values. So our next step is to do the mixing calculations of our outdoor air and our return air at these relative airflows. So we'll assume our air in our space, which is our return air state, is at a fairly standard indoor air condition. So we will assume a dry bulb temperature of 75 Fahrenheit at a relative humidity of 50%. And for our outdoor air, we will assume standard air conditions at some made-up location. So we'll just say, for this example, we have outdoor air dry bulb temperature at 87 Fahrenheit and a wet bulb temperature of 73 Fahrenheit. So with these values, we can determine the entire psychrometric states of our return air and outdoor air. So rather than doing all the math by hand for determining our total psychrometric state, we are just going to use the Heatwise online psychrometrics calculator. So we'll first enter our altitude, and you can see here we've got our first point with our indoor conditions that we specified, so 75 Fahrenheit and 50% humidity. And then we're just going to add a point, and this will be our outdoor air at 87.73. So we have our 2 points here, and as you can see, we can pull all of our psychrometric data from this online calculator here. So we will use these values here to populate the rest of the data that we need. So you can see here I've just populated all of our psychrometric information for the return air and the outdoor air. So to do our mixing calculations properly, we actually need the mass flow rate, not just the volumetric flow rate. So for each airstream, our mass flow rate is the volumetric flow rate over the specific volume. So for the return air, we have 4,500 over 14.46. And for our outdoor air, that will be 1500 over 14.91. So using the information we have now, we can plug these into our psychrometric calculations to determine our new enthalpy and our new humidity ratio, because those are just the weighted averages of the mass flow rates. And then we can use those values to find our new dry bulb temperature. So I've written out both equations here and plugged in all the values from our two air streams. And from these equations, we see results of 30.87 BTU per pound of enthalpy and a humidity ratio of 0.0111 for our mixed airstream. So using these two values, we can calculate the dry bulb temperature of our mixed airstream. This is using the enthalpy equation we learned in a previous video and rearranging to solve for the dry bulb temperature. So I've written out the equation here and plugged in the values, and you can see that with these humidity ratio and enthalpy values, we get a dry bulb temperature of 78 Fahrenheit for our mixed airstream. So just summarizing our total mixed airstream, now we can see we've got 78 Fahrenheit dry bulb temperature, 30.87 BTU per pound for enthalpy, and 0.0111 for our humidity ratio. And our mass flow rate is just the sum of our two mass flow rates that are mixing, so we're at 411.9 pounds per minute. The next step in our process is to dehumidify the air to the next state. So we'll call this our dehum state. And for this example, we'll assume that we're dehumidifying to a temperature of 50 degrees Fahrenheit. Since this is well below our mixed air state, we can fairly assume that the humidity will be basically right at the saturation curve. But we'll just say it's a little bit lower. We'll say about 95% Fahrenheit for this example, because we can't be right on the saturation curve. So we'll take 95% humidity as our second point, and from those two pieces of information, with the 50 degree Fahrenheit and 95% humidity, we can determine the rest of our state. And so we'll just do that using our Psychrometrics calculator on Heatwise and populate the rest of the data. We now know our starting state and final state for the dehumidification process. So based on these values, we can now determine the total sensible and latent cooling required for this process. So ultimately, what we want is the information necessary to size our air handling unit. So the air handling unit will consist of a fan and the cooling coil and the heating coil. So once we get the sensible and latent cooling values, then we can size our cooling coil. So if you recall from the previous video, we had equations for sensible and latent cooling. So first we'll start with our sensible cooling equation. We have our QS value is what we're looking for. And this is based on our CS value, airflow Q, and our change in temperature. We know our airflow and temperature values, but what we need to first think about is the CS value. So it starts at a 1.08. That's the default value from sea level. But we have our altitude adjustment for this example. We're at 1,500 feet above sea level. So using our altitude adjustment factor from before, we can adjust our CS value to a revised value of 1.02. And similarly with our latent value of CL, which starts at 4,840, revising it with our altitude adjustment gives us a new value of 4,583. This CL value is used in our latent cooling value, which looks very similar to our sensible cooling equation, but it is using the humidity ratio instead of our dry bulb temperature. So plugging in these values to our sensible and latent cooling equations, we get 171,360 BTU per hour of sensible cooling and 93,493 BTU per hour of latent cooling in our total dehumidification process. And adding these values together gives us a total of 264,853 BTU per hour for our total cooling load. And that is equal to about 22 tons. So we have about 22 tons of total cooling for our dehumidification process. So we now have a few pieces of information for our air handling unit. We know that we're doing 6,000 CFM of total supply air with 1,500 CFM of outdoor air. And we know our sensible and latent cooling requirements for dehumidifying the air to 50 degrees Fahrenheit. but we still need to reheat the air because we don't want to be supplying at 50 degrees Fahrenheit. So in this example, we'll be reheating it to a more reasonable temperature. So we'll be doing about 55 degrees supply air. 55 degrees is a more typical supply air temperature, and that's to help make sure that we're not overcooling the space in a sensible way after we dehumidify the air. So we now need to size our reheat coil to bring the air through sensible heating only from 50 degrees Fahrenheit to 55 degrees Fahrenheit. So to do this, we just simply use our sensible heating equation again that we used for our sensible cooling, but this time it's reversed. So now we're taking the same CS value of 1.02 and we're using our total airflow of 6,000, and we are bringing the air from 55 up to 50, a total heating of 30,600 BTU per hour. So we now know our reheat coil size, and that's the final piece for this air handling unit size. Summarizing our air handling unit, we now have 6,000 CFM of supply airflow. We have 22 tons of total cooling, which is split into about 171,000 BTU per hour if we're just rounding it, and about 93,500 BTU per hour of latent cooling. So we can size our cooling coil now because we know our sensible and latent values, because both of these are going to play a role in sizing that cooling coil. And we can size our reheat coil, which is going to be sized for 30,600 BTU per hour of total sensible heating. So that is the end of the calculations, but before we end, we should look at what this actually looks like on a psychrometric chart. So you can see I've plotted all the points here. We have our return state R and our outdoor air state O. Those mix to this mixing point M between the 2 points on the line connecting them. It then goes in a straight line from M to the point D, that's the dehumidified state, and then reheated from D to S. And our final supply state is at 55 degrees Fahrenheit at approximately 80% humidity. So that's just a nice visualization of what we've actually done. You can use a psychrometric chart to do all this whole process, or you can use the calculations and then see what it actually looks like to make sure it makes sense. So that is the end of this fourth and final Psychrometrics tutorial from Heatwise. I hope you enjoyed it, and we'll see you in the next video.